With a mission to map the rocks and layers beneath our feet, geophysicists face a persistent challenge: noise in our seismic data. So today we're looking at a technique called structure-oriented filtering that's helped out how we clean up our seismic image. It's a bit like having noise-canceling headphones, but for seeing into the earth. I'm Heather Beadle with the ASPE group at the University of Oklahoma. So when we collect seismic data, we're often dealing with terabytes of information from seismic waves, and the seismic data looks like this. What you're looking at here is a cross-section of Earth's subsurface. Those horizontal lines, those are the rock layers. But notice all the fuzzy noise. Some of it's random and some of it's systematic noise from things like our acquisition geometry. Here's the same data after structure-oriented filtering. The difference is clear. Well, if you're a seismic interpreter who's looking at higher frequency structure, and it's all done without losing any of the geologic features. So we can even look at the noise that we remove to double check that our algorithm didn't remove any of the valuable data. And this is always a good check for geophysicists to perform to make sure they're not over-filtering their data. So let's dive into how structure-oriented filtering actually works. It's a three-step process. In the first step, the algorithm calculates something called structural dip. So for each point in our data, it looks at the surrounding traces, and then it determines which direction the reflectors are trending. After that, it calculates a dip that follows the geology. So you can think about it as creating a map of how all the layers are oriented in space. So next comes the crucial part: identifying discontinuities. So we do this with a coherence method that calculates the similarity between the adjacent traces and identifies where abrupt changes occur. And so this will end up creating a similarity volume that highlights the faults, it'll highlight channels, and it'll highlight other stratigraphic boundaries. And these are all of the different features that we need to preserve in our filtering. In the next step, in the third step, we want to apply a smart filtering. So what we want to create is a filter that uses overlapping analysis windows, and it chooses the most coherent window for each point in the seismic volume, okay? And so what we want to do is we want to apply stronger filtering in continuous regions and then automatically reduce the filtering near edges or near those discontinuities that we just identified in the last step. And so one of the tricks that we use is called a Kuwahara filter. So imagine that you're trying to smooth data while preserving those important edges that tell you there's good geology there that you need to interpret. So instead of just using one analysis window that's centered on your data point, the Kuwahara filter looks at multiple overlapping windows. And so here's the key. Each window includes your target point in the data, but they're typically centered at different locations. We tend to start off using 9 to 13 overlapping windows. And so at each point, the filter will look at all of these windows. It'll measure which window has the highest similarity or lowest variance, and it'll use that window for filtering. So that works particularly well when a window straddles a fault, because it'll have a high variance or a low similarity, and so it won't be chosen. Rather, it'll choose a window that stays just on one side of the fault and select that window for filtering. So it's kind of like the filter is automatically trying to find the safest window to use and avoid smearing the data across these important features and discontinuities. So now let's look at a real-world challenge. So here's an example from the Gulf of Mexico. This is an early 1990s vintage data set from the West Cameron area. So it's a good place to demonstrate the method. We have channels, we have listric faults, and we have bright spots, as well as a strong acquisition footprint in the inline direction. So what we've got here are two different sections, one of the inline and one of a crossline. So now we can apply a simple filter along the structure. In this case, we're not worrying about the edges. Now we can look at the noise and see what was removed in that case where we didn't consider the edges. And what we notice is there's a bit of geologic information that's been filtered out. So now let's try it again, but we're going to use the Kuwahara filter and incorporate Sobel similarity. All right, so here we've got our new filter data that helps us see exactly more clearly where the faults are, where the stratigraphy is. And we can look at the noise with it and see that in this case, less geologic noise is removed. And so as we know, maybe, is the better amplitude data you have, the clearer seismic attributes you'll end up with. So we can now take our SOF filtered data and we can run some attributes on it. So here we're looking at the same data set, the energy ratio similarity at 2 different depths on the original data. And so we can see channels and we can see some faults throughout. When we look at it after running SOF, you can notice that the noise is removed and the edges of the channels and the faults are much clearer. So it's easier for us to interpret what we're seeing with confidence. So you can keep in mind that what you're seeing isn't just cosmetic improvement to make the seismic pretty, but by applying SOF, you're allowing clearer reflections to help the geoscientists. And with this data, we can do many things from identifying potential reservoirs to mapping our fault networks more accurately and make better informed subsurface characterization decisions. And so I hope you enjoyed this quick demonstration of structure-oriented filtering. It's one of the ways I like to remove noise from my seismic data. And you can feel free to reach out anytime, and we've got even more data and more details about how this method works on our website.